All right, let's take a look at problem 4. So problem 4 is very similar to problem 3. It's just the data we're given is presented in a slightly different fashion. And so the first thing I'm going to do is just take the information that we're provided with and try and sketch a basic TXY system for this VLLE system. We're dealing with two partially miscible liquids, and then discuss how we would use that information in terms of solving A, B, and C. So even before though looking at A, B, and C, the first thing I'm going to do is sketch a phase diagram, right? So it'll sound like a broken record, but I can't, overemphasize how important it is that you be able to sketch very simple phase diagrams. They could be invaluable tools in terms of cooking up solutions to your problems, not just in this chapter, but later on too, when you're dealing with, say, modeling your binary VLE systems using, say, excess Gibbs free energy models. Being able to check the reasonableness of your results, being able to just properly set up your problem and make sense of what you have. So, all right. So now we're modeling water and 1-butanol. So remember, homologous series of alcohols, methanol, ethanol, 1-propanol, 1-butanol. 1-butanol is where we start to exhibit partial miscibility, right? For alkyl chains less than 4, all right, so before less than 1-butanol, so 1-propanol, ethanol, and methanol are going to be completely miscible with water. All right, so we're told that water and 1-butanol are partially miscible in each other. At 1 atm, the two-phase system boils at 93 degrees C, and the composition of the three phases are this. Okay, so let me just create a sketch in general, then let's try and figure out what we have and label the data. Okay, so when I have a partially miscible system, okay, what I'm thinking of is a system, a binary system, that exhibits a minimum boiling azeotrope. So I'm thinking about a TXY phase diagram with a minimum boiling azeotrope. And then remember, since they're partially miscible, I expect a flat region of that bubble line. That shows to me that it's a heterogeneous minimum boiling azeotrope. Heterogeneous just meaning that we have two partially miscible liquids, right? And so in theory, at the azeotropic temperature, I have two liquid phases that could be in equilibrium with that vapor phase. Okay, so minimum boiling azeotrope. Let's say we're plotted with respect to the most volatile component. So most volatile component is going to have the smaller pure component saturation temperature. So this is T1 sat. Let's just draw T2 sat up here. Okay, so bubble line is going to be characterized as decreasing, have this flat region, and then increase until T1 sat. Bubble line, we're going to get these two lobes where my dew line pinches my bubble line. Okay, where my dew line pinches my bubble line, this is my azeotrope, and then these correspond to our two mutual solubilities. Or if we were to assume that the mutual solubility doesn't change much with temperature, I can draw two vertical lines down here indicating my phase boundaries in my liquid region. Okay, so now what do we have? We're told the boiling point of pure butanol is 117 degrees C at 1 atm, and I know water is going to be 100 degrees C at 1 atm. Okay, so T2 sat, so this must be 117.7. Okay, T1 sat must be 100. Okay, so if I'm plotting with respect to the most volatile component, I would have water as component 1 and 1-butanol as component 2. Okay, choice is rather arbitrary here, but you just need to be able to keep track of things. Okay, and then what we're given here, it's the same data. It's just a matter of if what you're labeling as component 1 or what you're labeling as component 2, right? Both of these are going to sum up to 100%. Okay. All right, so the two-phase system boils at 93 degrees C. Okay, so what that's giving us, okay, is the temperature of this flat portion of our bubble line. Okay, so the two-phase system boils at 93 degrees C. Okay, that gives us the temperature of that flat region, which corresponds to the temperature of our azeotrope, all right, at which we have the two mutual solubilities at that azeotropic temperature. Okay, so that's 93 degrees C. Now, we're calling water component 1 and 2-butanol component 2, labeling things with respect to the most volatile component. Okay, so that means I'm looking at, okay, my second line here. Okay, since I'm representing water as my component 1. Okay, so notice we have upper liquid, lower liquid, and actually the names are going to be slightly different. We'll kind of talk about what that means. But upper liquid and lower liquid, so composition of two liquid phases. Okay, so what that corresponds to is here. Okay, this is going to be 0.201. Okay, this mutual solubility would be 0.923. And then my vapor, right, this is going to correspond to my azeotrope, which is 0.445. Okay, so this they call the upper liquid phase. Wait, no. That they call the lower liquid phase. This is the lower liquid phase, and that's the upper liquid phase. Okay, and so basically what that corresponds to is 1-butanol is going to be less dense than water. Okay, so if I'm in this liquid-liquid region, okay, and so I get phase splitting, okay, I end up, so if I have, let's just say I have a mixture of composition Z1, okay, then I'm going to get phase splitting along my isotherm, okay, and I would end up with one liquid phase of this composition in equilibrium with the liquid phase of that composition, okay. So this left phase we would say is rich with respect to 1-butanol, right, because it would be 0.2 mole fracs water and 0.799 mole fracs 1-butanol, so it would be a 1-butanol rich phase, where this phase would be a water rich phase. And since the density of water is greater than that of 1-butanol, so if I were to have this system in a beaker, say it was closed and I could shake it up so I get phase separation, okay, this butanol rich phase is going to sit on top because it's less dense. So I'll have a 1-butanol rich phase on top and that water rich phase on the bottom. Okay, so they call it the lower liquid phase, right, because it's going to be the more dense one on the bottom. This, the upper liquid phase, because it's going to be the less dense system sitting on top, that oily phase. Okay, cool. Okay, so that's where the naming convention comes from. Where this comes from vapor. Okay, so again, if I had this mixture of this composition Z1, okay, and I heat it up to my bubble line, okay, if I heat it up to the bubble point for that mixture, okay, that's where the first bubble forms, my system first begins to boil. And actually, if I were to perform this experiment, it would be in theory pretty cool, because as I heat it up, right, I've got these two liquid phases. Picture my beaker, oil-rich phase, upper phase on top of my dense liquid phase. When I heat it up to my bubble point temperature, 93 degrees C, okay, so if I'm at this point, okay, to the left of my azeotrope, this liquid phase essentially disappears. The lower liquid phase essentially disappears, and all I'm left now is that oily phase. It would be in equilibrium with the vapor, right? And at the bubble point is the theoretical limit. So in theory, the lower liquid phase should disappear, and I just have that oily upper phase. And then as I continue to heat it up, I would have that upper phase, that oily phase, in equilibrium with the vapor. Okay, cool. So when they say the two-phase system boils at a given temperature, that's what they're referring to. If I had a mixture with the azeotropic composition in which I had liquid in equilibrium with the vapor, okay, and again if my mixture had composition of the azeotrope, and I heat it up, then I go directly from liquid, where I have those two liquid phases in equilibrium with each other, to vapor phase, right? I go directly from two liquid phases to a single vapor phase. Okay, so that's what they're getting at by the two-phase system boils. That's what all these points correspond to. And so then, in A, if we were to walk through this, the solution is formed by mixing 5 moles of water with 2 moles of butanol at 50 degrees C. So I'm at 50 degrees C, so I'm below that flat region. Assuming the mutual solubility of the two components at 50 degrees C is the same as at 93 degrees C. Okay, so that just means these phase boundaries are vertical. Mutual solubility at the azeotropic temperature would be the same as those at 50 degrees C. How many phases are formed? If more than one, indicate the composition and amount of each phase. All right, so basically you would just need to calculate mole fraction of butanol. So if I have 5 moles of water and 2 moles of butanol, well, it's with respect to water, so I'd have 5/7, right? So in A, say Z1 is equal to 5/7. Actually, so 5/7, 0.714. Okay, so Z1's 0.714. Okay, then what that tells me is I'm in between my azeotropic composition and my right phase boundary. So I'm in the LLL region, and so I will in fact get phase splitting. I'll get phase splitting to form 2 liquid phases. Okay, so how many phases form? 2. I'm going to be in the liquid-liquid region. What are the compositions of each phase? What are the compositions and the amounts of each phase? Well, I'm going to have to do a simple balance. Okay, so basically, right, because it wants amounts. Right. How many phases are formed? Indicate the composition amounts of each phase. Okay, so I'll get this eventually. So if I wanted to think of this like a flash problem, okay, and actually let me draw it down here. Okay, so we have Z1 is equal to 0.714. Okay, so basically I'm going to construct a flash drum. Okay, I'm going to send in a liquid phase, and I'm going to get inside my flash drum, you can think of it as being equilibrium contact, or I'm going to get VLLE, right, partial miscibility, or it's going to correspond to liquid-liquid equilibrium between the 2 exiting streams. So if I have some Z1 going in, which is 0.714, and that's going to have flow rate F. Okay, then coming off the top, coming off the bottom. So let's just use Y and X just for the heck of it. Okay, and let Y maybe be our water-rich phase. Okay, and let's let X be our butanol-rich phase. Okay, so basically, I'd be somewhere in between these 2 points. So let's just say 50 degrees C I know is below this dividing line. So if I had, say, this Z1, okay, and let me draw it in red so it kind of stands out amongst all the other ones. Okay, so 0.71 would get me somewhere around, say, here. Okay, so since I'm in the LLE region, so I know I'm between the azeotrope and this point, okay, but I will get phase separation. So I'll get phase separation along this isotherm, where using this notation I'll have this Y, okay, in the equilibrium with this X. Okay, so Y, okay, change the colors back, would be 0.923. X would be 0.201. Okay, and I'll label this as L and V. All right, so then the question is just, well, I don't know F, so I'm going to have to assume a basis. Or, right, I can manipulate it, right? But, so rather than assume a basis, so if we just assume you have 2 components, I can write down 2 mass balances, no reactions, I can write them as mole balances. So if I write down my total mass balance, L plus V, okay, component, mole balance, U1F is equal to X1L plus Y1V, okay. Okay, so I'll plug equation 1 into equation 2, so I can rewrite this as Z1 times L plus V is equal to X1L no. Oh man. See, the issue is I'm out of coffee for the day. All right, so so we could we need to assume a basis, right? It's inevitable, so we need to assume a basis. Because looking at it, I have three unknowns. I have F, L, and V. Okay, so we assume a basis, and so the basis I'm going to assume is I'll just assume that F is equal to 1. All right, so if I assume F equals 1, all right, then when I calculate L and V, right, it's relative to a value of F of 1. So it essentially gives me a fraction liquid and fraction vapor. Okay, so if I assume F is 1, then I know F, then it just leaves unknowns L and V because I know Z1, X1, and Y1. Okay, so assuming F is 1, then I could solve, because it wants the amounts, I could solve for, L and V, all right, the amounts in the two liquid phases. And then since I assumed F equals 1, right, I could say that's, the fraction, or, the amount of my butanol-rich phase relative to, that of my system. Okay? So assume F equals 1, you can solve for L and V, that's the, relative amounts in the butanol-rich phase and water-rich phase. Okay? Then B, if the mixture in part A is brought to boil, which liquid phase will disappear first? Okay, so what this is corresponding to is we said, okay, my mixture is going to be over here. Okay, so if I heat it up to boil, okay, what's going to happen is here I have two liquid phases in equilibrium with each other. Once I hit my bubble line, okay, now enter my VLE region, okay, I'm going to have this liquid in equilibrium with this vapor. Right, this vapor would correspond to vapor with my azeotropic composition. So I would have my water-rich liquid in equilibrium with this vapor. Okay, so in this context then, this butanol-rich phase would disappear. So again, the real picture is I have a butanol-rich phase on top of a water-rich phase. I heat it up. When I hit my bubble point, okay, what's going to happen then is my water-rich phase will remain, but my vapor-rich phase, or my butanol-rich phase, butanol-rich phase disappears, and I end up with that water-rich phase in equilibrium with the vapor. So we would say the butanol-rich phase disappears. And then C, it's desired to convert the mixture of part A into a single-phase solution. This could be done by adding more water or by adding more butanol. Calculate the minimum amounts of water and butanol that are needed to produce a single phase. Okay, and so basically what we want to do is, so if I start with this mixture here, okay, so component 1's water. So if I add more water, right, if I add more water to my system, that corresponds to increasing Z1, right? Z1's going to increase. So if I add more water, keeping the moles of butanol fixed, Z1's going to increase, okay? So that would correspond to moving to the right. And so what I want to know is if I start with a mixture of this composition, how many moles of water would I need to add to get myself to this phase boundary? Okay, how much water would I need to add until I hit this phase boundary? At which point I'll just end up with a single phase. All right, so this is also cool. I have the system in which I have one butanol-rich phase on top of a water-rich phase. So if I add water, okay, drop-wise, what's going to happen is that as I move closer and closer to this phase boundary, the size of that water-rich phase increases until the butanol-rich phase disappears. Okay, cool. Now you could go the opposite direction too, right? So if I were to add one butanol, that would correspond to decreasing Z1. So then you could also think of adding one butanol until I reach this phase boundary, at which the water-rich region would disappear, and I'd just be left with the butanol-rich region. Okay, so yeah, so basically starting with Z1, and you could take a basis, assume some initial number of moles of and not how much water or butanol do I need to add to push myself to either one of those boundaries. Okay, but again, this is another scenario where first thing I did was set up the problem, because once I had the problem, it became feasible in terms of coming up with a solution strategy to solve each case. So hopefully that helps.